So I want to take a moment to go through a couple of examples with absolute value equations. So we're going to talk about what the absolute value means and how we can set up an equation to help us solve set up two equations to help us solve equations that deal with absolute values and inequalities also that deal with absolute values. So first, what is the absolute value function? The absolute value function takes any number that's put in and it makes it positive. So if x is a positive or non-negative number, 0 or positive, the absolute value of x is just x. But if you put in a negative number, the absolute value is the opposite of x, so negative x. Basically, again, the absolute value function makes whatever number you plug in positive. If you put in a positive number, it stays the same. If you put in a negative number, it negates it. All right, we have talked about how to solve things graphically and numerically. To solve an absolute value function graphically or numerically, you will look at the table or the graph to help you solve. Also, I want to point out what the graph of an absolute value function looks like. The absolute value of x is this little v. And most absolute value functions, pretty much all of them, have a v shape. It'll be some form of this graph shifted up, down, left, right, or compressed or stretched a little bit. But the graphs of absolute value functions have these shapes. And then I'm going to just jump down to this section. How do we solve an absolute value problem? So with absolute values, we end up with two cases. Depending on if the expression inside of the absolute values gives us something positive or negative, we have two different things going on. So when we have the absolute value of x equals b, that means if we take what's inside of the absolute values x out, that term has to either be equal to b or equal to negative b, okay? If x equals b, the absolute value is, the absolute value is b. Or if x equals negative b, and if x equals negative b, the absolute value of x is b. So for absolute value equations, we're gonna use this property to help us solve. If we take what's inside of the absolute value symbol, I want to highlight, take what's inside of the absolute value symbol, and then you set that equal to the number that's on the other side of the equal sign and the opposite of that number. That gives you two separate equations, and when you solve those equations, you'll get your solution to the absolute value equation. All right. Example one goes with really, really, really easy examples. I want to do more interesting ones. So I'm going to scroll down a bit. Actually, it doesn't hurt to go over, I guess, an easy one. So we can look at this practice one really quickly. If we have the absolute value of x is equal to 8, then that means that x, the term inside of the absolute value, either equals 8 or it equals negative 8. Okay? For part B, this is very important. What if we have the absolute value of x is equal to negative 15? That doesn't mean x equals negative 15 or x equals positive 15. Remember, the absolute value function makes your whatever you plug in positive. So if you have your absolute value being equal to a negative number, like in this situation, that's not possible. The absolute value of anything is going to be a positive number or 0 sometimes, non-negative. So if you get a negative number, we say that there is no solution. All right. So I'm going to scroll down to the next practice section where we'll see more involved absolute value problems that we want to solve. All right, so here we have at the bottom here, the absolute value of negative 3x plus 5 equals 6. That means that this expression in the absolute value symbols, negative 3x plus 5. If the absolute value of it equals 6, that means that this expression equals 6, or the other option is this expression is equal to negative 6. Shouldn't write them under each other, I'll write them next to each other, sorry. and negative 3x plus 5 equals negative 6. So you take the term in the absolute value expressions out, and then you get these two equations that we can solve. There's never enough space below, so I'll write this at the top here. Right, solving these equations. Negative 3x plus 5 equals 6 gives us negative 3x equals 1, and then x would be equal to negative 1/3. That's one answer. And on the other side, if we subtract 5 from both sides, we get negative 3x equals negative 11, because you have negative 6 minus 5. And then dividing both sides by negative 3 gives us x equals 11/3. So these should be relatively easier 1 or 2 step problems to solve. But the idea here is we take what's inside of the absolute value symbol and set it equal to plus or minus the number on the other side of the absolute value symbol. And that gives us our two solutions, negative 1/3 and 11/3. All right, for part B, this one is a little bit more involved. We have the absolute value of negative 3x, and then plus 6 equals 12. Before we jump to the step that we did in the last part, where we take what's inside of the absolute value out and set it equal to plus or minus the number on the other side, first you need to isolate the absolute value term. So for this problem, we can subtract the 6 from both sides first. And we have the absolute value of negative 3x is equal to 6. 12 minus 6 is 6. Then at this step, we can break this into two separate equations. All right, so we'll have that our term inside of the absolute values, negative 3x, has to be equal to 6, and negative 3x can also be equal to negative 6. If that expression equals 6 or negative 6, then the absolute value is equal to 6. And then this equation that we started off with in the beginning will be true. All right, let's move this up again for having more space. If we solve this one, negative 3x equals 6, x is equal to 6 over negative 3, so x equals negative 2. And negative 3x equals negative, oh, I'm just rewriting it. Negative 3x equals negative 6. X would be equal to negative 6 over negative 3, which is positive 2. So our two solutions would be x is positive 2 and negative 2. All right, any questions about A or B before we go on to C? Now in C, look at this one. So much going on. One, we first have to isolate our absolute value term. So to isolate the absolute value term, we have to subtract 6 from both sides. This time, when we subtract the 6 from both sides, we end up with the absolute value of 2/3 x minus 5 equals negative 1. Remember, if you end up getting your absolute value is equal to a negative number, you can stop right there. This is not possible, so we would say that there is no solution for this equation. All right, so nothing to do there. And then for part D, the absolute value of negative 2x plus 3 equals 4. We start off by subtracting the 3 from both, look at the answer showing. We start off by subtracting the 3 from both sides. That'll give us the absolute value of negative 2x plus 3 equals 1. And then from here, we take what's inside of the absolute value symbols, and we'll set it equal to positive 1 and negative 1. Solving these equations will give us our solution. I should have enough space here. If we subtract 3 from both sides for the first equation, we get negative 2x equals 1 minus 3 is negative 2. And then dividing both sides by negative 2 gives us x equals 1. And then on the other side, if we subtract 3, we get negative 2x equals negative 4. And dividing both sides by negative 2 gives us x is 2. So the solution here is plus or minus 2. Also, just to be thorough, we can talk about how to solve these graphically as well. So I'll just do part D. We'll solve part D graphically. If you want to solve anything graphically, which we talk about for all different types of functions, graphically always means find the graph, or graph both sides of your equation, I should say, and find the intersection point. So for part D, if we're solving graphically, we would let y1 equal the absolute value of negative 2x plus 3, and then we'll let y2 equal 4. This is to solve graphically. Okay, once you have those two equations in, you then find the intersection. And in this case, notice we got 2 answers, so that means that there should be 2 intersection points. We'll look at the graph of this to show why. All right, so we're going to graph absolute value of negative 2x plus 3, and then 4. Let's go to Desmos. Functions. Sorry, I have to find absolute value on here. Where is it? I know it's on here. Oh, right there. Looking in the wrong place. All right, so the absolute value of negative 2x plus 3, and then I'm going to close those absolute value symbols, then plus another 3. See, we get this little V-shaped graph here. Let me make it a little bit bolder. There we go. This is what the graph of the left-hand side of the equation looks like. On the right-hand side of the equation, we have 4. So I'm just going to put in y equals 4, so we get that horizontal line. And then we can see very clearly here that there are 2 intersection points. The first intersection point is at 1, 4. So that's why we got the solution x equals 1. And the second intersection point is at 2, 4. So that's why we get x equals 2. I'll zoom in a little bit here. So the line crosses the absolute value graph, which is in the V shape, in 2 places. And the x coordinate gives us our solution. All right, any questions about this? Okay, then let's go to our lab from last class to write up the solutions for that. And we'll jump into our new material next. That was lab 3.3 to 3.5. All right, so in the last class, we talked a lot about solving inequalities, regular inequalities and compound inequalities. And basically we said it's pretty much exactly like solving an equation, except 2 big differences. One, your final answer won't just be 1 number or 2 numbers, it'll be an interval of numbers. So we need to know how to write out the entire interval of solution possibilities and also how to graph that. And then the other difference is the steps. When you're doing the steps for solving the inequality, if you multiply or divide by a negative number, that changes the direction of your inequality. Okay, so those are the 2 things you need to look out for. All right, solving these problems, you can check your work as we're going through. Like I said, I know a few people had issues accessing this lab. It was saying that it was locked or something. So some of you may not have been able to submit it on Canvas by the end of the day last time, but that's okay. Like I said, anybody emailed me their work, I will accept that as well for this lab. All right, then where do we go? First problem. we have 5 minus 2x is less than or equal to 1/3 x. If we have an inequality with fractions, we can start off by finding or multiplying by the LCD to clear our fractions. The LCD in this case is 3. So if you multiply everything by 3, we have 3 times 5 minus 3 times 2x is less than or equal to 3 times 1/3 x. That gives us 15 minus 6x is less than or equal to x. All right, then from here, we can move all of the x's to one side, all of the constants to the other. Technically, it doesn't really matter what side you write them on, but usually people find it easier to write your x's on the left and your constants on the right. Doesn't matter though, it's up to you. I am going to, it doesn't matter. I'm gonna add the 6x though to both sides. Yeah, I like the way that looks. Then we have 15 is less than or equal to x plus 6x is 7x. And then finally, if we divide both sides by 7, we get 15 over 7 is less than or equal to x. Now you have to be careful with the way that this is written, because usually when we read inequalities, we read them from left to right, and we want our x to usually be on the other side. So we can write this the other way also. This is also saying that x is greater than or equal to 15 over 7. You can write it either way. We need to be able to write this in interval notation. That means that our answers are numbers bigger than 15 over 7, and we have an or equal to signs here, so it includes 15 over 7 as well, bigger than or equal to. So we'll start at 15 over 7, and then go all the way up to infinity. We always put parentheses around our infinity symbols, and this time we'll have a bracket around the 15 over 7. Then on to, well, we're going to do C because it's next to it, and then we'll go down to B. For part C, -2 is less than or equal to 3 minus 2x, which is less than or equal to 3. We have a compound inequality here. We want to try to get what's inside of the, what's in the middle of the compound inequality. We want to simplify that so there's just an x in the middle, okay? We can start off by subtracting, zoom out a little bit, subtracting 3 from each part of the inequality. That will give us -5 is less than or equal to -2x, which is less than or equal to 0. And then we have x being multiplied by -2. So we need to divide everything by -2. Be careful. Remember, when you divide by a negative, that changes the direction of your inequality. So we'll end up with 5 over 2 is greater than or equal to x, which is greater than or equal to 0. Again, we normally like our inequalities. You want to make sure you're able to read this. When you write out your interval notation should go from the smallest number to the biggest number. So in this case, I'll write this the other way. This would be 0, the smallest possibility, is less than or equal to x, which is less than or equal to 5 over 2. You can have it written either way. And then in interval notation, this tells us that we're starting at 0, going up to 5 over 2 for our solution. Both of these include the or equal to symbol, so we'll have closed brackets around both sides. Then on to B, we're solving the or inequality, the or inequalities. 1 minus x is less than or equal to -2, or -x is greater than 2. So remember, for an or inequality, our solution set is going to be all x values that are in either of the solutions to either of these inequalities, okay? So we'll solve both of them and put the solutions together. This first one would be, we subtract -1, -x is less than or equal to -3. And then if we divide by -1, so we subtract 1 and then divide by -1. That'll give us x is greater than or equal to 2. All right, x is greater than or equal to, did I mess something up? Oh, yes, sorry, -3 divided by -1 is 3. That's what I messed up. So x is greater than or equal to 3. That's our first solution. And the other one tells us we just divide by a -1. X would have to be less than 2. All right, so we want to put these things together. And then we also want to think about when we write out our interval notation, we start off with the smallest intervals and go to the largest ones. So saying x is less than 2, that means we're going to have everything from -infinity to 2. And then for the other part, x is greater than or equal to 3. That's starting at 3 and everything bigger than or equal to 3. All right, putting these two together though, okay? We start with the smaller interval, -infinity to 2. And then we're going to use this little u symbol called the union, and then put the next interval, 3 to infinity. If those intervals overlapped, then we would be able to, I made another sign error, you guys. I'm so sorry. It's an easy fix though. Here, when you divide by a negative, we switch the sign, but that should be a -2. This should be a -2. This should be a -2. My apologies. The intervals still don't overlap. If they did overlap, we could combine it to a smaller interval, but since they don't, we'll just combine them using the union symbol. All right, and then the last one. Part D is an AND problem. Our final answer for part D has to be only the x values that are in both of these solutions, okay? Or the intervals for both of these inequalities. For the first one, if we solve, we have 2x plus 2 is less than or equal to -3. Subtract 2 from both sides, that's 2x is less than or equal to -5. And then dividing by 2, x is less than or equal to -5/2. Okay? And then for the other one, we multiply everything by 2, we get -x plus 14 is greater than, what's it greater than? 4. And then from here, we subtract 14 from everything, we get -x is greater than -10. All right, and then dividing by a negative, x would be less than +10. All right, for this one, I think it'll help us to draw the number lines so that we can see exactly what's going on here. All right, so I'll do some color coding. If we have our number lines, it doesn't have to be exactly drawn to scale, but -5/2 is going to be to the left of 10. All right, so the solution for, or drawing the solution for x is less than or equal to -5/2. We're starting at 5/2, it's included, and then we shade in everything less than this. Okay, for the other one, x is less than 10. We have an open circle around 10, and then we shade in everything less than this. Now here's where we have to pay close attention. Our answer is going to be everything that's covered by both the green line and the pink line. The things that are covered by both the green line and the pink line are these values. -infinity up to -5/2, including 5/2. So that's the solution. Because this is an AND problem, our solution has to work for both of these. All right, so it would be -infinity to -5/2, including the 5/2. And what about all of these numbers over here? Why don't they work? Well, it's because any value bigger than -5/2 will be a solution to the second equation, but it won't work for the first one. And for an AND situation, we need it to work for both of them. Then let's knock out the rest of this. Problem 2 gives us 2 absolute value equations to solve. So remember, we isolate the absolute value symbol or absolute value term, take what's inside of the absolute value and set it equal to plus or minus the number on the other side of the absolute value. So for part A, it's already isolated. We have 1 minus 2x equals 7, and 1 minus 2x equals -7. That gives us negative 2x equals 7 minus 1, which is 6. And dividing by negative 2 gives us x is negative 3. On the other side, when we subtract our 1, we get negative 2x equals negative 8. And then dividing both sides by negative 2 gives us x equals 4. So our two solutions are negative 3 and 4. All right. Then for part B, we have to do a little bit of work before we isolate, or before we can isolate the exponential term. I keep saying exponential when I mean absolute value. It's my second time with that mistake. I won't make it again today. All right. The absolute value term needs to be isolated. We'll subtract 4 from both sides. That gives us 3. Absolute value of 5 minus 2x equals 6. And then if we divide both sides by 3, the absolute value of 5 minus 2x would be equal to 2. And then at this point, we can break this up into two equations. 5 minus 2x equals 2, and 5 minus 2x equals negative 2. That gives us negative 2x equals 2 minus 5, which is negative 3. So x would be equal to 3 over 2. And for the other one, negative 2x equals negative 7. So x is equal to 7 over 2. So 3 over 2 and 7 over 2 are our solutions. All right, then last part is a graph. So for our visual learners, this will probably be a little bit easier for you. I want to get a brighter color. So using the graph, we can see that f of x is that increasing line, g of x is the decreasing line. We're asked to use the graph to solve the inequalities. For part A, we want to know when f of x is greater than 0. That means when is f of x above, for what x values is f of x above the x-axis? That means that it's greater than 0. We can see here that f of x equals 0 at negative 1. And then for everything after negative 1, the graph is above the x-axis. So we would say our solution is negative 1 to infinity. All right, for part B, we want to know when g of x is greater than 0. We look at g of x, that's the decreasing line. We see g of x is equal to 0 at 2. And then for numbers less than 2, the graph is above. I need a brighter color. That's better. For numbers less than 2, the graph is above, or for x values less than 2, the graph is above the x-axis. So our solution for part B would be negative infinity all the way up to negative 2. All right, for part C, we want to know when are f of x and g of x equal to each other. That's this intersection point, which has coordinates 1, 2. So the x value is our answer. When x is equal to 1, f of x equals g of x. And then for part E, when is f of x greater than g of x? So we want to look at the lines and we want to know when is the line for f of x above the line for g of x. So starting at that intersection point, we see to the right of that intersection point, f is above g. Okay, so if f is above g after that intersection point, that means that we're looking at x values that are bigger than 1. So from x equals 1 all the way on, f of x is greater than g of x. So our solution there in interval notation would be from 1 to infinity. And then last one, I'm running out of colors. We can use yellow. When is f of x less than g of x? We look the other way, starting at this intersection point. For all of the values less than 1, the g of x function is above f of x. So g of x is greater than f of x, or f of x is less than g of x for all x values less than 1. That would be from negative infinity to 1.